Hello and welcome to part 3 of the video series Vectorization, Loopless Coding in Python for Data Science. In this particular part, we are going to see a very interesting example, and we will basically write its vectorized code in Python. And the problem is that problem basically appears in a lot of contexts in computer vision, and this problem is known as corner detection in images. The version we will be using is basic Harris corner detector, but the goal in this video is not to learn how the corners are detected and is not to learn the mathematics of the underlying mathematics of the corner detection. Rather, we will be looking this problem completely from the programming perspective. So I'll be explaining what are the steps in detecting a corner without actually explaining without actually justifying why those steps are there. I'll be just explaining the steps, and then we will be trying to write an algorithm, or then we will be actually writing a code to achieve the solution for that. And we will be trying to write the code completely loopless. So what happens is, given an image, so you can think image as a 2D matrix, a matrix with some rows and columns. So given an image, so let me call that image as I. We have to convolve that image with x derivative filter. Let me define that filter as -1, -1, -1, 0, 0, 0, -1, -1, -1. Let's say this filter. And we have to convolve that filter, and let's say the result is ix. Then we have to convolve this, this image with a y derivative filter, which is -1, -1, -1, 0, 0, 0. It depends upon what conventions of x and y you're using, because changing the convention may change this to iy and this to ix. It completely depends what conventions of x's as x-axis and y-axis you're using. So once we have this ix and iy, again, this ix is again m by n image. That's m by n image, and similarly iy is also m by n image. Now our goal is basically to construct the following matrix for each pixel. So for this pixel, for this pixel, for this pixel, and so on. So let me consider a pixel i, j. And for that particular pixel, we want to do the following processing. And remember, we have to do this for every pixel because every pixel may be a candidate corner pixel, and following is the computation for one pixel, and we have to do this for every pixel. So for I, j entry, what we really want to, we want to construct a matrix. Let me call that matrix as it is sometimes called the structure tensor. Let me call that T. That matrix is basically the following. It is Ix, Ij, it's square, and then we have this Ix, Ij times Iy, Ij, and then we have this basically Ix, Ij, and Iy, Ij, and this is Iy, Ij, and this is square. That's a 2 by 2 matrix, and this is for this particular pixel. Not only that, we have to build this matrix in such a way that we actually have to pick some of these. So in the neighboring window, for example, u varies from -2 and v varies from -2 to 2, for example, and 2 for a 5 by 5 window, or maybe a 3 by 3 window. And we actually have to, so this entry actually changes to ix, I plus u, and j plus v, and then square. So every entry actually changes. So what we really want to do is we want to pick this entry and its neighboring entries, and we want to add them up, and that will be eventually one number. And similarly, we want to do the same with this particular thing, and that, and that, and that will be one structure tensor, one matrix for this particular pixel. And we want to generate these matrices for every pixel. So considering again this ij pixel, let me call this as Tij, that's a matrix. Next, what we really want to do is we want to compute the eigenvalues of this Tij. So consider this matrix as Tij as a matrix like A, B, B, and C. The computation of eigenvalues are the following. So the formula, the characteristic equation looks like A minus lambda C minus lambda minus B square equals to 0. And here we will be applying a perfect, that's a quadratic equation in lambda, and we need to compute lambda here using maybe perfect squares or something like that. But that we have to do for every pixel. This is for ij, then a next pixel and a next pixel and so on. And for every pixel, this Tij matrix will be different. It might be different. And we have to do that. So the goal is to iterate over this image for every pixel, generate this matrix, and compute the eigenvalues, and then obviously thresholding the smallest eigenvalue actually give whether it is a corner or not. But the goal is actually to compute eigenvalues for structure tensor of each pixel. Now it looks difficult to not apply a loop and still we are able to find out this matrix for every pixel. And then subsequently we have to apply, because we want to compute the eigenvalues for each of these entries. Let's see how can we code this, the whole problem, how can we code that completely without loops. Yeah, that's interesting. Let's go to Jupyter and actually code this interesting example without loops. So let's now build a solution for this problem. Let's import certain packages that we need. Import numpy as np. For convolution, let's use signal from SciPy. So from SciPy, import signal. So that's all that we need. Let's import these libraries, and I guess they are imported now. And let's generate an image just randomly, np.random.rand. And let's say this image is, let's generate an image, let's say 32 by 32. Let's generate that image, random image. Further, let's generate X mask and Y mask. So X derivative mask. So let's say mask X is np.array. Let's generate that, which is, for example, -1, -1, -1, -1. Then we have 0, 0, 0, and then we have again -1, -1, and -1. Let's have this mx, and my is simply the transpose of mx, so mx.t. So now we have these available. Let's now compute ix, which is the x derivative. Here I have used a 3 by 3 window for derivative. You can use, there are several techniques for computing derivatives. So here I'm going to use the signal.convolve2d. So convolve 2-dimensional, and I want to convolve this I with mask mx. I want to keep the boundary as symmetric, just to focus on, for example, on the border pixels, and I want to compute this, the resultant image size should be the same as the original size, so same. So that's my ix. Similarly, I can just generate iy from there. So iy is the same thing, with exception that it is generated by mask y, and the rest of the things are, the code at least is the same. So that's ix and iy. Now the problem is we really want to have, for example, this particular matrix that we saw here, this particular matrix. Actually, this matrix requires ix squares and ix iy product and then iy squares, and it actually picks a neighborhood of these matrices and build this particular matrix. So what we now do is we basically first generate ix square matrix, ix iy matrix, and all these matrices separately, and then we will see how can we avoid looping this and we still be able to find out this these eigenvalues. So let's first build ix square, which is just ix into ix. This is not matrix multiplication, this is just pointwise multiplication. So iy square, which is just iy times iy, ix iy, that is simply ix times iy. So now we have all the things that are available. Further, let's define, because we are going to add in a neighborhood. If we for example have all these matrices and we have defined the same, let's say 5 by 5 neighborhood, what we can do is we can convolve our ix square image with a mask of all ones and convolve this particular matrix ix iy with all the mask 5 by 5 mask of ones. Then convolution of that basically gives us the summations at every pixel. Now every pixel will be having a summation on the neighborhood. So now what we can do is we can have sum in the neighborhood of ix2, that is signal dot convol. Let me make a mask of ones as well. So mask of ones, masks is np dot ones, and let's say this mask is 5 by 5. So that's our mask. Now what we do is we convolve all these images with this mask, which will take care of the summation that is there inside the matrix. So sum of ix2, sum in the neighborhood of ix2 is signal dot convolve 2d, and we have this ix2 and we have mask m, and we need the boundary to be symmetric at the borders, and we need the output size to be the same as the input size. So that's about this matrix. So then we have the same about y2, except that now we are using this matrix, and then we have the same as for one other matrix, which is ix iy. So let me write ix iy, and this is ix iy, and the rest of the story is exactly the same. Oh, I have some issue here. ix2 is not defined. Oh, that is not 2. That is, I mean, there is no square there. So yeah. Now I'm going to actually show you some of the things that we will need to avoid this final loop over computing the eigenvalues pixel by pixel. Now consider this particular entry at location ij as A, this particular entry as B, and then these entries. So let me now move towards, so let's say at Tij location, at Tij we compute the following matrix, which is sum of ix2 ij, and this is sum of ix iy, that is ij, and this is again sum of ix iy ij. I guess I have I have taken this as 2. Let me this 2 is not there. This is not square. So this, and then we have this iy2, and this is ij. And now we can pick for every I and j, we can pick these entries, and we are just good to go and compute the eigenvalues on every I and j, and we are just good to go. But we want to avoid this loop over I and j for final step. So how can we move on? So consider, for example, this matrix Tij has entries A, B, B, and C. Then the eigenvalue computation like in our previous slide, like we saw in our previous slide, has to solve this equation where B is basically this entry, A is basically this entry, and C is basically that entry. Now this solution can be written in the following form: lambda square minus A plus C lambda plus AC minus B square, this matrix, equals to 0. And here, if we consider this as the linear term and this as the constant term, the final solution, let me call this A plus C as, let me call this matrix as D, and let me call this final matrix, this particular matrix as F, for example. Then the final solution, lambda, can be written as minus D plus minus D square minus 4. And this A is simply 1 for, so that is A for A, and this F, just the formula, over 2A. That's the formula. We can apply this formula, we can apply this particular formula element-wise, or we can apply this formula on the whole matrices, and that will compute the eigenvalues for every matrix. Not a big deal. We can apply this formula for a plus value and for a minus value, and these will be the two eigenvalues, and thereby avoiding this loop over index I and j. How cool is that? So let's go to Jupyter Notebook and actually code this stuff. Remember, this A is this thing. So A plus C is D, and this is the entry A, and this is the entry C. So we will go back and forth on this slide, and so let's compute A. So first of all, A is all ones. So np dot ones, and it requires the six2 dot shape, whatever the shape is. So that's our A. Now what's our D? Let's see. What's the capital D? That is A plus C, and this is A and this is C. So we have to add this one, and that will be D. So let's compute D. So D is six2 plus sy2, that's our D. Now we really want to compute F, which is A times C minus B square. So A times C minus B square. So let's see that. So F is A. So let me write that. A. So this is not capital A. So this is six2 steric siy2, that is A times C in our matrix, minus B square. So minus B, which is sixiy steric sixiy. So that is our F. Now we have all our matrices available with us. Now we are ready to deploy the formula to compute the lambda value. So let's say lambda 1 is, if we see the formula, that is minus D plus D square minus 4AF over 2A, which is minus D plus D square minus 4 steric A steric F, and we need to have the square root of this, which is this, and then the whole term is divided by 2A, 2 steric A. So this one. So that's the lambda 1 for every pixel. Oh my god. Then we can compute lambda 2 for every pixel without a loop. That's amazing. That's just minus there. And that's the lambda 2. So that's it. Now you can find out which one of these is maximum. There are some positive semi-definite matrix properties here. We can compute which one is maximum, which one is minimum. The final steps in corner detection is to pick the minimum eigenvalue for each pixel and just threshold it. If it is larger than a threshold, then that's a corner, not otherwise. But we are not interested in, for example, for this particular part of the video, we are not interested in solving the corner detection problem. Actually, we were interested in writing the code for the corner detection problem that is loopless. And here you can see there is no loop in the code. And the hardest part to avoid the loop is the final part, where we actually build this Tij for every pixel, and then we need to compute the eigenvalues. And there we did this completely through a vectorized variant. We need not to iterate using a nested loop of I and j. So that this final two equations may give you a much more understanding of what vectorization is. We haven't iterated over arrays through indexing through loops, and still we found what we really needed to find. So that's about it. I guess you might have enjoyed this part as well. So if you like our content, please press the like button, and do subscribe our channel, and share this material with your fellows. So hope to see you next time.